So let's quick talk about the problem between multiple comparisons. So to address the general question of whether there is a relationship between two categorical variables, we look for significant differences among the conditional distributions of one categorical variable given values of the other variable. So the null hypothesis always is going to state that there's no relationship. So I would say my H naught, there is no difference in the distribution of a categorical variable for several populations or treatments, right? So our null hypothesis, for the example from the previous video, would there be no difference in the distribution of whether they have considered themselves have or have nots for several political ideologies, right? That's what I could test. Ideologies, right? Our alternative hypothesis says there is a relationship between the two categorical variables, but doesn't specify any particular type of relationship. So our alternate hypothesis is there is a difference in the distribution of a categorical variable for several populations or treatments. So from our previous example, there is a difference in the distribution of have or have nots for several political ideologies, right? Now, we could compare many pairs of proportions ending up with many tests and many p-values, and that's a bad idea, right? That's too many probability tests. So when we do many individual tests or confidence intervals, the individual p-values and confidence levels don't tell us how confident we can be in all of the inferences taken together. So not just comparing the haves between the political ideologies and the have-nots, like we need to compare everything. So the problem of how to do many comparisons at once with an overall measure of confidence in all our conclusions is a common in statistics, right? This is the problem of multiple comparisons. And statistical methods for dealing with multiple comparisons usually have two parts. So the first one is an overall test to see whether there's good evidence of differences among the parameters that we want to compare. And the second would be detailed follow-up analysis to decide which of the parameters differ and to estimate the degree to which they differ. The overall test, although much more, straightforward, or much more complex than the tests we met earlier, is reasonably straightforward, but the follow-up is what can be quite elaborate is the follow-up. So in order to start with this, we need to talk about to build up to doing a chi-square test, we first need to talk about expected counts in two-way tables. So our null hypothesis is there's no relationship between two categorical variables that label our rows and columns of a two-way table. And to test our null hypothesis, we compare the observed counts in the table with expected counts. So these are the counts we would expect if our null hypothesis were true. And if our observed counts are far away from our expected counts, that's evidence against our null hypothesis. Now, how do I go about calculating an expected value, expected count? Expected counts are also sometimes called expected values. So the expected count in any cell of a two-way table when H naught is true is that the expected count equals my row total times my column total divided by my table total. So let's go back to the have not versus political ideology table we looked at before and calculate some expected values. So finding the unexpected count is not that difficult, as the following example illustrates. So our null hypothesis is that ideology and have-not study is there's no difference in the distribution of have-nots, whether it's a conservative, moderate, or liberal. And to find the expected counts, we start by assuming H naught is true, and we see from the two-way table that 1,062 of the 1,867 surveyed consider themselves haves, right? So our total number of haves out of our total would be 1,867. So if ideology has no effect on have or have-nots, then they're saying that the proportion of those that we should have for each ideology is 1,067 over our like total. So it'd be 56.9%, right? Would be halves if this was true for everyone. So, get more up here. Okay, so the overall proportion of those saying they're a have should be 1,062 out of 1,867. There we go. And for those, the expected counts for each ideology are the following. So we'd take 725 times that 0.56 to get 412.4 moderates. Conservatives, and 357.79 moderates. Okay, so I took, for this first one right here, I took my row total times my column total over my everything total. And then for moderate, I took my row total times my row total, that's this one, times my column total over 1867. And then for liberal, I took my row total times my column total over 1867. And that's how I got those values. Those are our expected values. Now we're going to use our expected values to calculate our chi-squared statistic. So the chi-squared statistic is this. So we want to test whether the observed differences among our conditional distributions are statistically significant. And the test statistic that makes that comparison is a chi-squared statistic. So what it measures is how far our observed counts would be from expected counts if our null hypothesis were true. So to calculate our chi-squared statistic, we take our observed count minus the expected count. So we'd take like our observed count in our table, which for conservatives was 460. This is for the conservative halves. Well, that's not a good example. Minus the expected count squared over the expected count, and then we take the sum of every single one. That's what this sigma means. This means sum. So I have to take it for every single row and column. So every single square in our data. And the sum is over all the cells in the table, which is what I just said. So typically you're going to want to do this using technology. You can do it by hand, but I wouldn't recommend it, right? So because this test for relationship, if the test is significant, it's important to look at the data to learn the nature of the relationship. And we have 3 ways to look at the data. So we can compare selected percents. We can compare observed and expected cell counts. That's what I like to do. And we can look at the terms of the chi-squared statistic. So which cells contribute the most to the value of our chi-squared. So we can use technology to find the p-values for us. The p-value for a chi-test comes from comparing the value with the critical values for the distribution. So here are distributions, and much like the t-distributions, they have degrees of freedom. So the chi-squared distributions are a family of distributions that take on only positive values and are skewed to the right, and it gives us, it changes based on its degrees of freedom. It becomes less skewed to the right the more degrees of freedom we have. So to calculate the degrees of freedom, what we do is we take our row total minus 1 times our column total minus 1 to get our degrees of freedom. And that's how we determine the p-value in our area, because the greater my degrees of freedom, the more spread out my chi-squared is going to be. So the chi-squared test, like the z procedures for comparing two proportions, is an approximate method that becomes more accurate as the counts in the cells of the table get larger, okay? Higher degrees of freedom. But we're lucky that chi-squared approximations are accurate for quite modest counts. You can safely calculate the chi-squared test with critical values from the chi-squared distribution when no more than 20% of the expected counts are less than 5, and all individual expected counts are 1 or greater. So in particular, all 4 expected counts in a 2 by 2 table should be 5 or greater. 2 by 2 being like the smallest table we could make. A 1 by 1 table wouldn't make any sense, really. And note that this guideline uses the expected cell counts, so that's expected cell counts, not observed.